and clear peaks at 3.1 GeV, so which was interpreted as E plus and minus is from decay of a single particle. This is tau lepton, and you see Martin Pearl. So here are events which we have discussed when E plus or E minus and mu plus appear with loss of the energy. Essentially, this is just reactions which we have discussed. This is discovery of boson quark, and you see here Leon Lederman and Appel and Lederman unfortunately passed away just very recently. You see here, and he got actually Nobel Prize also for discovery of muon neutrino. Here you see with a good resolution 4 peaks I have discussed before, this epsilon 1s, 2s, 3s, and very wide peak for 4s when we have decay into 2 pions. Sorry, when we have decay into B mesons, so this is 4 still. Now, gluon discovery. So this is Petra, and this is Hera accelerator complex in DESY in Germany. It was, now it doesn't exist. This is the detector, and you see here these 3 jet events. Now you see really what are these jets. So these are tracks, and you see they grouped in 3 families, so 3 groups. And so this is more intensive, and most probably this is quark, and probably this is gluon track. I don't know precisely. And this is quark, which actually emitted this gluon. This is how it looks like in reality. So this is just repetition in this jade detector. Neutral current. Remember, I said very briefly that was already discovery, which confirms the standard model, which predicted existence of neutral gauge bosons, and therefore one expects neutral current events when you have muon neutrino or muon antineutrino scattered on electrons via exchange of Z0. And this is bubble chamber Gargamel, and it is staying at CERN. So one you can see if you visit the CERN, and that's how it was when the experiment was running. So muon neutrino beam from accelerator, and then what they have studied in this bubble chamber recoil electrons. So here are events. So let me see if I have somewhere marked what are. No. So you see how many tracks, and I have forgotten. I think once I think that one is event not for scattering on electrons, but also neutral currents in scattering on nucleons, and that probably event here. I think this one is the track of electron, recoil electron. Intermediate boson, again, so very briefly, because I haven't discussed this time, you will have exercise for the next week to write the production of W boson in terms of structure functions of proton and neutron, and these are detectors UA1 and UA2. 2 detectors were used in SPS experiments, so they have this synchrotron SPS, which actually is working now, and he is pre-accelerator for LHC. But these detectors do not exist anymore, and you see here UA1, which is under Carlo Rubi, and this is UA2. That's already quite big scale, so here you see the person staying in the accelerator. So this is, you see Carlo Rubi, who is celebrating discovery of W boson and Z boson. Now this is one of the events with discovery of W boson, and you see here the track. I think this is muon track, and just single track, you know, not compensated by anything from other side, so which means from another side you have neutrino. So that's event when W boson decays into muon and a neutrino, and you see the track. Now this is discovery of Z boson, which is easier, and you see here 2 tracks, which are, so that's that one and another one. And this is probably mu plus, mu minus, I think, because there's a big penetration. So Z0 decays in mu plus, mu minus. And these tracks are not along one line because Z0 is moving. So probably it's moving in this direction, and therefore the events are not back to force each other. So this is discovery of Z boson. This is tevatron, where top quark has been discovered. I think I showed already this picture. And this is the ring, and this is inside the ring of tevatron. This is CDF detector, which actually used to discover top quark. Here's the size. This is typical kind of setup of these detectors, which is kind of onion structure. There are different detectors, one inside another, to detect different components of events. This is D0, another detector which also aimed at detection of top quark. So there are two detectors. Now this is top quark discovery. And this is kind of messy event, and yellow tracks show probably the relevant tracks which then were used to reconstruct the invariant mass. By the way, in this Z event, when you saw these two tracks, what people did they measured the invariant mass of the pair and so on, then reconstructed Z0. So that looks how this event, you know, I don't know how to interpret. So some jets, muon, missing energy, and I told you probably that it was something like several years just to analyze events. So they recorded this, and during several years analyzed events. So this is again top quark event, some tracks, and this is how they represent these things. And you see that's the beam is moving in this direction, and you see here some kind of these squares which actually indicate the energy release in different directions. So using this, you can reconstruct what happened, which kind of the event happened. This is the experiment to detect tau neutrino donut. This real size, not a big experiment, not big size. And this is one of the events. Remember, I said that these are events with kinks. And you see here one of these kinks. So that's inside the detector. What you have here, interaction of tau neutrino. And these are hadron tracks. And you see it's not everywhere this sensitive volume. There are these plates, and in these plates they see some energy release, and therefore they reconstruct the tracks. And you see here the kink. So this is the track due to tau lepton, and here tau lepton decays into, this I think is a muon or electron, and here is of course tau neutrino and other stuff which is missed. Now LHC, since I have not discussed discovery of Higgs boson, that should come after, of course, this standard model. I'll just let me flash. This is how accelerator looks, and you see there is proton-proton collision, and in the same kind of tube you have two pipes for two proton beams moving in different directions. And of course they intersect in certain ranges. This is Atlas experiment. Again, very complicated structure. This is CMS. Now, that's how it looks like. This is Higgs boson event, and Higgs boson event, you see, that's very kind of clear when you have two gammas. Remember, one of the channels Higgs boson was discovered is decay of Higgs boson in two photons. Then you can easily reconstruct invariant mass. These are more complicated events. I think here is the event when Higgs boson decays in Z and virtual Z, because mass of two Z bosons is bigger than the mass of the Higgs boson. So one should be virtual, and then these Z zeros decay into leptons. So you have four tracks here. So this is LHCb. I mentioned it. Aimed at studies B mesons. Now, parity violation. Here you see T.D. Lee and C.N. Young. I think that's the time when they actually proposed explanation of this tau theta problem. And here's Madame Wu doing this experiment. So this is another photo. This is already later. And you see here Pauli with Madame Wu, and this Madame Wu is doing her experiment. This is how experimental setup looks like on the right-hand side, and this is what we have discussed. So cobalt decays asymmetrically, and you see B is magnetic field, and the nuclei is polarized along B direction, and then more electrons are seen in direction down. So these are some drawing of her experiment. I don't want to go into details. And this is CP violation, and you see here Cronin and Fitch, and they got a Nobel Prize for discovery of CP violation. I don't think that I have more slides on this. And this is something which I will discuss today. So here you see again super Kamiokande detector, and we will have exercise actually concerning this detector. So this is huge instrument. This is 50 kiloton of water. This is Cherenkov detector, and you see here photomultipliers attached to the balls of this detector, so they see Cherenkov light emitted by particles moving inside. So it's filled in by water. I will talk about atmospheric neutrinos. I said a little bit more. So unfortunately, I first show the slides, and then we'll discuss what is this. So atmospheric neutrinos are produced in interactions of cosmic rays with atmosphere. So this blue is atmosphere, and what happens is that secondary particles include pions, which then decay, emitting muon neutrino and muon in turn decays into electron, and then the muon neutrino and electron neutrino. So in each of these events, you have production of 2 muon neutrinos and 1 electron neutrino, and you expect the ratio of a muon to electron fluxes in the detector of the order of 2. So, and super Kamiokande detects these events. So I will show you the reactions later. And even before Kamiokande, super Kamiokande is later detector, Kamiokande have seen not 2, but something around 1, which actually was the first hint that something is wrong with muon neutrinos, and then it was established that muon neutrinos are oscillating into tau neutrinos. These are events. I think I showed already this before, and so these are mu-like events when muon neutrino interacts to produce muon in final state, and then you see some tracks, some rings which correspond to muon and to electrons. So they detect mu-like events and E-like events, and they can then see the ratio of these events, and the ratio was of the order of 1, so close to 1, instead of being 2. So that was one of the indications. This is super K result. I explained this dependence, but just to remember, so these are real data, and the cost is Nobel Prize for these measurements. So you see here data or predictions as the function of L over E. So this is the distance neutrino travel over the energy of neutrino. And what you see here is first is at low small l over E, it's of the order of 1, which means there is no any effect. This is what you expect. But then there is a dip. And then this curve approaches something like 1/2. Just remember this, and I will then discuss later what is the meaning. And these are experimental points. You see, these are real data, which then we're used to. Now, this is another detector, which I will talk about today. This is Sudbury Neutrino Observatory, an SNO detector. You see here, it is filled by heavy water, and so you see it's surrounded by, so this is the working detector, and it's surrounded by another sphere and photomultipliers again attached. And everything is in light water volume, and everything is deep underground. So this is the way how solar neutrinos were detected. And here are some parameters, about 1 kiloton of this heavy water, which means D2O instead of hydrogen, deuterium. Well, some parameters, if you are interested, I can discuss this later. This is solar neutrino spectrum, and what probably you can remember from here, the energy range is say from 0.1 to 10 MeVs. Actually, this is 14 or 15 MeVs with different components. These are SNO events. Again, they see this Cherenkov radiation, Cherenkov rings, I will discuss this later. And also remember this picture, because this is what happens inside the sun. You produce electron neutrino, which has this composition. I will discuss later what is this. And then when it propagates from high density to low density, what happens is that these are wave packets. So the wave packets, the size of the wave packets doesn't change. You see, so the upper and this is down. And there are two wave packets, because we deal here with mixing, with a mixed state, which is composed of two eigenstates. In vacuum, it's mass states. In matter, there are different eigenstates. So what happens is the size of these wave packets doesn't change. However, colors change, and colors means a mixture of electron and muon. So, for instance, in the upper wave packet, it's mostly electron neutrino with some admixture of muon and tau. And here, when density changes, the flavor of eigenstate changes. So this is what is called adiabatic conversion. And this is another example. When we have higher energies, at higher energies, something like this happens. Second wave packet actually can be neglected. And so you have propagation of this state which changes the flavor. And this is what happens inside the sun. And this is Kamland, finally. This is Kamland detector. And now it's also operating, but it searches for neutrinoless double beta decay. So it was first planned to study anti-neutrino interactions with just usual inverse beta decay from many reactors in Japan. At that time, reactors were operating. It was before Fukushima disaster. So after that, now it doesn't, nothing works essentially. So you see here scintillator detector, 1,000 tons of mineral oil inside. The diameter is 18 meters, and it is viewed by photomultipliers. And so they see energy release, events which actually consist of just energy release inside. And there are 53 atomic reactors contributing to this with average distance 180 kilometers. And what they saw a distortion of the energy spectrum. Remember, and you see here in this plot, this dashed line corresponds what you expect for number of events without any oscillations. And you see it is distorted, and there's a deficit of events with kind of oscillatory dependence. This is essentially the same in survival probability as the function of L over E. And you see clearly here oscillatory curve, which is discovery of oscillations. And here you see Kajita-san and Art MacDonald from SNO experiment, and Kajita from Super K, and they got a Nobel Prize in 2015 for discovery neutrino masses and mixing and oscillations. I think that's it. Questions? Okay. So. No questions? I hope I convinced that it's not a joke. It's not what we are studying is particle physics, right? This is the basis of our knowledge. It's amazing that we built so nice theory on just using these events like this, some jets or some tracks there, here, some rings. And it's amazing if you look at this. What this is experimental basis. So if you don't believe in the theory which we have now, try to invent something else which actually can reproduce all these events. So this is the point. Of course, every time people try something else. So what I'm discussing is just correct solution, right? But you should imagine that at each point there were many models. Now, for instance, we are working on this flavor and neutrino mixing, and we have 1,000 models. 1,000, imagine. I mean, in 50 years probably from here, it will be just a single theory, correct one, and someone will give lectures and explain, oh, this is how it works. But you should remember the hundreds of thousands of papers written on the models of neutrino mass and mixing, and and everything is just disappeared. And that was similar, not to such an extent as now, even before. So it's method of trial and exclusion of wrong decision. This is how we came eventually to the present interpretation, which it seems really correct one. Okay, so I'll switch. Oh, maybe, I don't know. Switch later. So today we will discuss lepton mixing and neutrino oscillations. Well, sometimes you are saying neutrino mixing, but what is important that it is not just neutrino, it's relative rotation of charged leptons and neutrinos mass states in the currents. And therefore it's not make sense to say just, oh, neutrino mixing, because as always charged leptons should be involved in this. So we have three doublets of leptons. And we refer to E, mu, and tau as muon, electron, muonic, and tau flavors. So flavors. Correspondingly, nu E, nu mu, and nu tau are neutrino states with definite flavors. Actually, there is a difference from quark sector, because in quark sector we usually refer to color, to flavor as the states with definite masses. So you're saying U quark, D quark, S quark, charm, they are particles with certain flavor. Here, we refer to flavor of a neutrino state which is staying in the same doublet or form the same charge current with electron. And neutrino flavors have no definite mass, in contrast to quark sector. Okay, so we have three flavors. We have three neutrinos with three different flavors. In terms of mass states, and let me write it, we introduce mixing. And we use this U instead of V, and here is electron, and you can similarly write other doublets. So what eventually has been established that electron neutrino, muon neutrino, and tau neutrino have no definite masses. However, they are combinations of states nu1, nu2, nu3, which have definite masses, and these are mixing parameters. And as in the case of quark sector, these parameters form the matrix, mixing matrix. And in the lepton sector, we call this U, P, M, and S. And let me just put this UE1, UE2, UE3, this U1, etc. So this is what we call Pontecorvo Makina Kagawa Sakata mixing matrix. Again, it is correct to say leptonic mixing or lepton mixing because these are two bases of mass states, and we have mass states electron, muon, and tau, and what we have relative rotation. So it's a relative rotation is important. Actually, you can bring this mixing to charged leptons, so you can write this, and the physics will be the same. You can write mu1. However, here you can write 1e, mu e, etc. Combinations of charged leptons. Probably that will be useful because some question always about oscillations of charged leptons. Yeah.
This is very similar to what we have in CK and
Yes, absolutely. Yeah.
Is there any natural relation between them?
That's a good question. What we have found, and eventually I will conclude, that the mixing is very different in quark and lepton sector. it seems that there's no trivial relations. And that is not established. So I believe that there are some relations. For instance, you may ask some other person and he will tell you something else, maybe. So what I will discuss mainly, and for simplicity, two neutrino mixing. For us it is enough. I will not discuss CP violation. Actually, CP violation hasn't yet been established in lepton sector, and this is one of the main goals of neutrino experiments, to measure CP violation, like in quark sector. So I will discuss two neutrino case, and so I will use electron neutrino, which is C mu1 in most of the cases, plus S mu2, and orthogonal combination, and I will denote this as nu A, because in practice it is some combination can be written as of nu mu and nu tau. Then it will be more or less a realistic case. So here minus S mu1 plus C nu2. So let me repeat again. Fortunately, we have this hierarchy of mass square difference and masses probably, and that simplifies consideration. So in many cases, the three neutrino problem can be reduced to two neutrino problem. And so this is why I will expose some material using two neutrino case. So see here cosine theta, and theta is mixing angle, S is sine. Okay? So there are different consequences of existence of mixing and neutrino masses. So how we can measure neutrino masses and what are manifestations? One is distortion of, yeah?
I just think that the class is not being recorded.
Really?
Like, okay,
Huh.
thank you.
So existence of non-zero neutrino masses should actually be seen in some kinematics of the processes. And one of these processes is beta decay. And in beta decay, you have spectrum like this. But this is for massless neutrinos. And the end point is the difference of masses of nuclei which participate. If you have non-zero neutrino mass, then you would have a cut of the spectrum. So with neutrino, if mass is non-zero, you would expect a lack of events at the end point, right? This is precisely because you have mass of neutrino and it takes some energy, and this is energy of electron, and this is number of events, and this is beta decay. So one of the consequences of existence of non-zero neutrino masses is change of kinematics of beta decay, so that your end point on maximal energy of electron is smaller than the energy of difference of the masses. So that P electron or energy, let me put here, energy of electron maximal is given delta M, and this is mass difference of nuclei minus mass of neutrino, right? So there were several experiments in attempts to really detect neutrino masses, and this year the experiment in Karlsruhe with the name Katrin start to operate. We may see some data, say within 5-10 years. And they have sensitivity to mass of neutrino of the order of 0.2 electron volt. And the present day bounds on the mass of neutrino from this type of the experiments is 2 electron volts. So that one. Much stronger bound follows from neutrino oscillations and from cosmology. Another consequence of mixing is decay. So neutrinos will decay if they have masses. And so heavier neutrinos can decay into lighter neutrinos. So like in our example, nu2 can decay into nu1 plus gamma. And let me write the diagram for this. You have nu2. This is W boson. This is gamma. And here you may have electron, muon, and tau. And here you have mu1. And this is because of mixing. Because here you have these mixing parameters. Here it will be UE2, for instance. So I think it's conjugated. This type of the diagram is not only of the higher order. You see here the loop, and this is W boson. But it also has gene suppression. So when you sum up, in the same way as we discussed gene suppression for K0 into mu plus, mu minus, when you sum up diagrams with E, mu, and tau, so they cancel each other up to the difference of the masses of charged leptons. Another mode of the decay is that mu2 can go into 3 mu1. And the process is quite similar. Now we have here W boson, nu2, nu1, but here is Z0, which then decay into nu1 and mu1. So you have 3 neutrinos, one should be antineutrino. You have 3 neutrinos in final state. So in the standard model, due to all these kind of suppressions, including gene suppression, the lifetimes is enormously big. It's much bigger than the age of the universe. So if, however, there is a new physics, the decays may be much faster. Actually, this type of the diagram is also a diagram for neutrino magnetic moment. And there is a very interesting and important phenomenology related to existence of large magnetic moment of neutrino. Unfortunately, again, in the standard model, the prediction for magnetic moment of neutrino is very small. However, if there is new physics, then that may be enhanced. Yeah.
Again, if the lifetime is too long, so can we try to detect this oscillation from?
Not oscillation, decay. Now we are the same.
Yeah. Decay. I mean, from the early universe neutrinos.
Well, again, you see, if you find some mechanisms which enhance decay in early universe, then it may happen. So that is kind of not clear, but the lifetime is bigger than the age of the universe. So, which means that if you just take this as it is, then you do not expect substantial effects. I think it's many orders of magnitude bigger than the lifetime of the universe. I don't remember. I think 10 to the 26 years or something, at least. And so it's 10 orders of magnitude bigger than the lifetime of the universe, starting from Big Bang. Now, of course, in the early universe, you may have some changes of this. But as far as I remember, actually, when I was working on this, I have forgotten already the results. You need to take here not just the vacuum propagators, you need to take propagators of particles in medium. But it doesn't change substantially the results. So, which means that unless you have some new physics, there's no hope to detect this type of the decays. Okay, now let's go to oscillations. And let me tell you that in most of the textbooks, oscillations are described in quite a confusing way. And mostly this is because the authors want to make this faster, to make it shorter. And then every year people produce, or young people produce some new papers just because oscillations are exposed in confusing way, and then there are always some questions, and then they write papers saying that, well, one needs to change the theory of neutrino oscillations just because of confusing description. So I will try to present here a minimal version without any conceptual problems. Okay? So I think this is the simplest way to expose oscillations without facing any conceptual problems. Oscillations of neutrinos is an amazing process. This is quantum mechanics at macroscopic scales. Can you imagine that you have 100 kilometers between the source and detector, and you can describe the process by propagator. Can you imagine propagator, you know, the size of 100 kilometers? Or the wave packet, which may have the size of few meters, and you can stay inside the wave packet of neutrino. So that's really very interesting stuff. So I will use again two neutrino case. So suppose we produce electron neutrino in beta decay. This means that we produce the composite state in a sense that it has two components with two different masses and with the mixtures given by cosine and sine. Well, actually, one first point I should make, this is electron neutrino in Lagrangian or in current. This is what happens, what appears in the current, charge current. In reality, you need to compute the state which you are producing in the process, and that can be written in general as in the following form. You produce the state, which can be written as cosine, again, mu1. Let me write here wave function, psi1, xt plus sine mu2 psi 2 xt. So, for instance, imagine that your energy release is smaller than the mass of second neutrino. Then you simply do not produce your second neutrino, and you will produce just part of this state. So in general, because of difference of masses, you will have different kinematics for production of nu1 and nu2, and so that is described by, in general, different wave functions here, 1 and 2. Again, you consider the process, like for instance beta decay, and you need to compute what is the amplitude of probability of production nu1 and what is the amplitude of probability of production of nu2 separately, using this expression which is staying in the current together with electron. In most of the cases, you can neglect difference in production of nu1 and nu2. Because of mass difference is much smaller than the energy released. But in principle, you need to take into account, keep in mind that a possible difference here. This is especially important if you introduce some new neutrino states and people are introducing sterile neutrinos or something else, some heavy neutrinos, then it is important. Okay, so that is, let me put here also T. So for production moment, you have, for instance, nu E, you have this nu x0, right, in moment of time. If neutrino is produced in the point 0, so it's 0. So this is what you are producing. But then neutrino evolves, and you have time dependence and x dependence in this wave functions, psi1 and psi2. So let me summarize. Psi I, and I is 1 and 2, are wave functions of mu I. And in initial state, you need to compute, using the amplitudes of production for this process, what are these psi1 and psi2. In most of the cases, psi1 in initial moment is very close to psi2 in initial moment. Well, I can put it still 0. Suppose it's produced in the origin. Okay? So these are wave functions, or when we consider propagation, we usually refer this to wave packets. So these are essentially wave packets. Clear? Okay. Now, wave packets can be parameterized in the following way. It has the form of the product of two factors. One is shape factor, and the second one is phase factor. So this is shape factor. Of your wave packet, and this is phase factor. So let me put here also I. Shape factor is normalized in such a way that the integral from minus infinity to plus infinity moduli square fi xt moduli square dx is 1. Then we have a correct normalization of total wave function. Okay? And in the most of the cases, these shape factors are the same for nu1 and nu2. The shape factor, in turn, is the function of certain combination of time and distance. Fi equals Fi and x minus v group velocity I multiplied by t. And that describes propagation of the wave packet. So you have something like that x, and you have this shape factor. And this combination means that, say, maximum of this shape factor, its position changes with time, and this is the group velocity. That means that this wave packet propagates with group velocity, as it should be, right? So this wave packets propagate with group velocity. Vj, which is equal dE over dP, and that is approximately P over E, and the group velocity is smaller than velocity of light. This can be strictly derived, but I'm just using this physical argument that this should be described by, so this is a shape factor. It should describe propagation of your state. So here is the phase factor, which means that actually you have something like this. You have oscillatory pattern inscribed in this shape factor. Okay? Well, actually, I'm using still some simplification here because, of course, you need to have kind of symmetric up and down, and not only this, it's even complex here. So, but this is good representation which is needed to understand the oscillation. So you have oscillatory pattern which is inscribed in the shape factor. So what's going on? This wave packet moves, and actually this picture, oscillatory, is moving with phase velocity. So what happens is you have this kind of wave packet is moving, and the oscillatory pattern is moving even inside this shape factor because it has phase velocity. Okay, so phase velocity is velocity with which, for instance, this peak is moving. and group velocity with which this peak, which is shape of the wave packet, is moving. Clear? Okay, good. Now we have mixed state, and therefore our electron neutrino should be described by two wave packets. One is for nu1 and another for nu2. And then our electron neutrino has the following form, following representation. That's the wave packet which corresponds to nu1. And I include this cosine and sine. And then the second one is described by this wave packet. And so they are having this oscillatory patterns according to this expression. So I multiplied here by cosine. This is multiplied by cosine, and this is sine. Otherwise, they would have the same shape. So what happens is that this kind of the system is moving. Of course, they are overlapping. I just showed this to see what's going on, but they are overlapping and interfere. So these oscillatory patterns in this wave packet and this part, they interfere, and the interference leads to oscillation. So this is what oscillation. Oscillation is a consequence of this interference of waves in the packet 1 and packet 2. Let me tell you now, in most of the textbooks, you will find either point-like description, but this has no sense, because if you have point-like points, you know, nu1 and nu2 are just point-like objects, then because of difference of masses, they have different group velocities and they stop to overlap. There is no oscillations, right? There is no overlap, there is no interference, there is no oscillations. Another picture when people are using plane waves, just plane waves. Also wrong, because you have then infinite plane waves, and then you have continuous overlap, and in fact, eventually is integration over this. And so then that actually produces already a lot of confusion. People invent some new theories. Here there is no problem. So what you have here, you have this finite size. So what is important? Finite size. Not infinite, not point-like, but finite size of the object. Wave packets. And what you have here is the following. Because of difference of group velocity, first of all, because of difference of masses, m1 is not equal m2, and that has two consequences. So maybe I should write it here. Maybe I should take still. You have this. You have different phase velocities. And therefore, interference picture will change with time, right? So you have different phase velocities, and therefore these oscillatory patterns will start to, to shift. And so the phase changes, and this actually leads to oscillations, as you will see. That leads to oscillations. But also due to difference of masses, you have different group velocities. This means that these wave packets as a whole will move with different velocities. And at some point, they will stop to overlap. So for instance, if this one has higher velocity, then after some propagation, you will have a picture like this. Right? So if this group velocity is bigger than this one, so then we will have such a picture after some time. They stop to overlap, they stop to interfere, and then oscillations just stop. Yeah.
When they stop the overlap, is this still a one particle when we observe, or?
Yes, that's still one particle. That's kind of interesting thing because you have kind of entanglement of these two things, which means that if, for instance, you will detect nu1 in your detector and you know that you detect nu1, that this collapses. I don't know if you know this terminology. Then you will not absorb already nu2. Okay, yeah?
The widths of the wave packets also keep the same amount all the time?
Now, the width of the wave packet, okay, good. So let me denote this, sigma x. Actually, this is determined by the process in which you are producing, at the conditions of production, the wave packet. This is determined by energy and the space uncertainties of the production process. So that's wave packet. Now, correct? Also, due to propagation and due to non-zero neutrino mass, it will be spread of the wave packets. Spread of the wave packets. I made these computations for solar neutrinos, and it turns out that solar neutrino wave packet changed by 4 orders of magnitude, so they spread 4 orders of magnitude while traveling from the sun to the Earth. But in most of the cases which we'll discuss, that will not be very important. Okay? So that's also the third effect, right? So now let us consider the phase factor, which is important for oscillations. We can write it, the phase as energy, actually some average energy in your wave packet, minus P average x, right? So that's how we define the wave, the phases. And so those are average energies in the wave packet. Actually, wave packet is, superposition of different waves, right, with different energy and momentum. This is how wave packet is formed. What I have written here, oscillatory pattern for average energy and average momentum. Okay? What I will assume also that the wave packets are not very big, so that when you compare the phases here and here, they are the same in this wave packet and in that one, because the wave packet is narrow. Otherwise, you would have different phase differences in the beginning and the end of the wave packet. But I will specify it a bit more later. Now, let us compute the phase difference, which is F2 minus F1. What people are doing, in many textbooks, you will find the following. So let's take equal energies and then compute what is this phase difference. And then every year people writing the papers, so why the equal energy, when in general if you have wave packets you have ensemble of different energies and different momenta. And so something is wrong, it looks like. And for this reason I give a general consideration. When I'm not assuming equal energies in two wave packets or equal momenta. Well, actually, this is determined again by conditions of production of your wave packets. And you need to compute, in principle, these average energies. So, delta F can be written as delta E time minus delta P x. Delta P, and I'm not assuming that neither this nor that are zero, or general. So actually, finally the conclusion is the following. If you take equal energies, you will still get correct answer. If you take equal momentum, you will still get the same equal number. And if you can take any combination, then you will still get the correct number. But this assumption is not justified. This is what I want to say. So what is delta P? Delta P can be written as dP over dE minus multiplied by delta E. And again, P is square root of energy squared minus mass squared. Right? So if it's I, it's I, it's I. Plus differentiation of dP over d mass squared multiplied by delta m squared. So let me see if you agree with this. Since P is the function of energy and mass, then in general the difference of momenta equals this derivative times delta E, this derivative times delta M. So using this expression for P, you can do this explicitly, and let me find the final answer for delta F. So I compute delta P according to this expression and insert here in this above formula. And now what I will get is that the phase difference equals delta E multiplied by T minus X V group plus delta M squared 2P multiplied by X. So this I will get if I insert delta P here, and I make computation here of delta P using this expression for the momentum as a function of energy and mass squared. Okay? Please repeat this. That's trivial stuff. So this is what is usually used. Everybody is using this. This is what is standard phase or standard contribution to phase difference. It is proportional to delta M squared, which is clear. If you have equal masses, then you have no phase difference. It is inversely proportional to momentum or energy of neutrino. But there is this additional factor. And in most of the cases, it is very small. So again, V group is P over energy. Delta E here is proportional to delta M squared over energy. So again, remember, these are average energies in your wave packet. And of course, if delta M squared is 0, then you would get the same average energies in your wave packet. So, and just on dimensional ground you can find this, but you can do this in a more precise way. So, delta E is proportional to delta M squared over energy. Now, what is this? This is T minus X over V group. I can multiply by V group velocity here, then I will get here X, and here is V group velocity over T. This is proportional to sigma X. Do you understand this? So since everything is propagating, within this shape factor, I remember we have written the shape factor, then X is given by V group average here, multiplied by time. And therefore, within the wave packet, X minus Vg times T is approximately sigma X. This is the feature of the size of the wave packet. So, since we have everything is concentrated in the wave packet, within the wave packet, the difference of T and X over V group should not be bigger, or it's of the order of sigma X. just look back to this picture. This is what we have introduced before. So the middle of the wave packet is given by group velocity in a given moment of time, is given by group velocity multiplied by time. So particle is not localized. It is kind of, can be here, because the physical meaning of this is the amplitude of probability to find particle in this state or in this state or in this position, right? And therefore, deviation of x from this average value is not bigger than the size of the wave packet. And therefore, this factor is of the order of sigma x, and therefore the product is given by delta m square over energy, and here is sigma x. And compare now with this term. Here we have x, and x can be, I don't know, 1,000 kilometers or 1,000 meters if you want. And here is the size of the wave packet. And okay, again, it depends on the process, but it can be 10 to the minus 8 centimeters, 10 to the minus 10 centimeters, maybe a little bit more. So clearly this term dominates. But what is important that this is much smaller than 2 pi, because you know, if you change the phase, although this is very big, however, if this contributes more than pi, then you need to take into account this. So, what I will use condition which is usually satisfied, that sigma x is much smaller than E over delta m squared. And under this condition, the first term can be neglected, and therefore delta phi equals delta m squared over this result 2 moment or energy multiplied by x. And delta m squared is m2 squared minus m1 squared. Now we will see later that this is actually nothing but oscillation lengths, well, with some coefficients. And therefore this condition is reduced to the condition that the size of the wave packet is much smaller than oscillation length. So you'll see oscillation lengths again, maybe 100 meters, maybe 100 kilometers, and of course this condition in most of the cases is satisfied. By the way, the physical meaning of this term, and suppose we have not small contribution, suppose this is not small, is the following. So sigma x is determined by the region in which your neutrino is produced. So what you do, you have the source, you have the nuclei, you localize this in your source, and therefore there's some uncertainty, right? You don't know if your nuclei is here or there, so there's this uncertainty. And it is this uncertainty which actually defines sigma x. Now, depict in this way. So your nuclei is somewhere localized, and this is sigma x. And the point is that it can decay in this position, but it can decay when it is here or there. And therefore that leads already to some oscillation effect, a difference of oscillation effects. One is if particle decays here, another is here, and there is some small difference which is quantified by sigma x. So essentially this term is equivalent to averaging of oscillations over production region, which has some physical meaning. So it's not just some junk. It has some physical meaning. In most of the cases it is negligibly small, but if not, then the meaning of this term is that it actually takes into account that some oscillation effect already occurs within the production region, inside your source. And not only from and in the distance between source and the detector. Good. And now, yeah.
So it's, you said that the neutrino oscillation may depend on the source of
May
may depend on the source.
Observable effect, yes. It depends on configuration. If you have very big source, okay, so there are different averaging effects, different, but briefly, I will kind of return to this question later. Yes, the observable effect of oscillations do depend on the source. No? So now let us derive the probability. Well, unfortunately, all this is needed to really to avoid any conceptual misunderstanding. But this is the simplest. Actually, one can use field theory to make these computations, really. It's more complicated, and but still we can do this, describing everything in the field theory. So, oscillation probability, or probability of transitions. We have our state, which has the following dependence on x and t. So we have cosine mu1 plus sine mu2. Let me write and then I will comment. Exponent minus I delta f. So I assume here for simplicity that f1 equals f2. This is shape factor, and it equals f. In most of the cases I will discuss that actually acts. So there are two extreme cases which actually really realized in the nature. Either you have complete overlap, and so you can say that my shape factors are the same, or you have complete loss of coherence, like in the case of solar neutrinos. When solar neutrinos are propagating from the sun to the earth, their wave packets are completely separated, so the coherence is lost. And that simplifies things. So here I assume that the shape factors are the same, which means that the distance between source and the detector is not so big. So they also production is quite similar, and so they overlap. It's not only they change the shape, but they almost everything so overlap. Now I put it out. Here what I write is the following. So delta phi is phi2 minus phi1. And what I did, I put out exponent minus I phi1. So what matters is difference of the phases, not the phase itself. And even if I keep this exponent I minus I phi1, eventually it disappears when I compute moduli square. Okay? Now the amplitude of transition of, for instance, nu e to nu a in our system is given by matrix element nu a, nu x t in the moment of time x and time t. Now remember that nu a is orthogonal combination, and it is given by cosine mu2 minus sine mu1. And we have orthogonality of states with definite masses. So these are different particles. Using this form of nu a, using this orthogonality, and inserting into this expression for amplitude nu a from here and nu xt from here, I will get the amplitude in the following form. It will be f minus sc plus sc minus ef delta f. Okay, let me now explain different terms here. So F is clear, it just comes from this new T. Now the first term comes when I take what? I take new one here and take new one here. So I need, of course, to take the same mass states in here and here because of orthogonality. And that will give for me S minus S and cosine. So this is the first term. The second one is when I multiply this new 2 onto this new 2. And then I will get here again sine, cosine, and then phase factor. And there is no cross terms here because new 2 here multiplied by new 1 here gives 0, and this multiplied by this gives me 0. Clear, right? Yeah.
Up to this point, when we talk about neutrinos, we always talk about electron, muon, or tau neutrino.
Yes.
Experimental point of view is when we detect the neutrino, we look at this source where the kink or where the reaction happens, and then deduce what kind of neutrino it is, right?
Yes.
There is no other. So now we introduce new mass states which are different from that flavor kinds of neutrinos.
Yes.
And is there any good reason to do that, experimental or theoretical? Like now when we talk about neutrinos in this setting, we refer to mass states.
No, look, here I compute new A, which is flavor state again. So the point is that what I detect flavor state. Because I'm using certain interactions, for instance, interactions with electron or, say, inverse beta decay. And in interactions, I always detect not mass states, but flavor states. I detect electron neutrino, and you are saying muon neutrino or tau neutrino. And this formalism takes into account. And for this reason, I actually what I'm doing, I'm computing the matrix element between this guy, which was produced. So I assume here that in the initial point, this is electron neutrino. So I produce electron neutrino, and then I can find what is appearance of other neutrino species. And this is what I can detect. Yeah?
So these V1 and V2 are abstract states that reproduce the mixing results.
What?
Abstract states that we don't observe.
Well, I don't call this abstract. These are physical states. So again, what we are considering in terms of mass states propagation. So the best way to consider propagation is to use mass states, because these are eigenstates in vacuum. So if you consider especially propagation in vacuum, then of course it's better to do this in terms of mass states, because we know how they are propagating. Nothing happens here. So new one is propagating, new one. The only what happens is appearance of the phase. And of course shape factor can change, but we are neglecting for the time being. Okay? So again, this is transition of new E go to new A. This is what we are computing. Interaction in terms of flavor states, because flavor states are eigenstates of interaction, if you want, right? So it's eigenstates of charge currents, and therefore this is what we are here detecting. Propagation, better to use to look at this in terms of mass states. It's usual. That's now. So what I can then write is minus F S C, then 1 minus exponent minus I delta F. Right? And then the probability is given by moduli square of this matrix element, and I need to integrate over time. So what happens is that I have my detector, and then this neutrino system is moving through my detector, and therefore I need to integrate over time if I'm not following the time. So of course if I arrange also time detection of my events, then it should be something different. Otherwise, I just know that my detector is staying at the distance L from the source, and I don't care about time. Anyway, it's very short. and just integrate over time. So which means that the probability of transition of nu e to go to nu a is given by integral over dt. And I need to use this matrix element, nu a, nu L. So if my detector is at the distance L from the source, moduli square. And in principle, I should integrate from minus infinity to the plus infinity, but I don't care about the time. Of course, it's a very short period when my wave packets cross the detector. Okay? So we have the source, and we have the detector. Suppose we have here nu e produced, and our detector can be arranged to detect nu mu, like for instance what we are using now in long baseline experiments. Or vice versa, we can produce nu mu and then detect nu e. Now the probability then can be right. I continue just the line before, dt minus infinity plus infinity. And then I insert expression for my matrix element, and what I will get is s squared cosine square 1 minus e delta phi square, and moduli square of my shape factor. It's L and T. Okay, moduli square. Now, if the phase difference is the same along the wave packet, it changes with time, but within the wave packet, in both wave packets, I have the same phase difference. Is the same. Then this factor can be put out of the probability, and what I will get is sine square, cosine square go out, 1 minus I delta phi moduli square, and then the integral dt moduli square of f L t moduli square. Okay? Now, you can compute explicitly what is this, and you find that this moduli square is equal to just 4 sine square delta f over 2. I don't know what this explicitly, but you can check. Okay? Now let me consider this integral, and this integral is from minus infinity to plus infinity dt moduli square, and here's f, and my shape factor is the function of L and T in the following combination, as we discussed already: group velocity time moduli square, and then changing variable from integration from, so I can integrate over this factor. What I will get is eventually 1 over G group, integral from minus infinity to plus infinity, but now over the distance, over kind of all these terms, I denote it by Z, dz, and I will have here f z moduli square. And this is just 1, right? Because we introduced this normalized in this way. Oh, sorry, this is V, right? So V, and I will take here approximately 1 group velocity. At this point, it is not important. And so finally, I get for probability the following expression. So factor of 4 then multiplied on this will give me sine squared to theta multiplied by sine square delta f over 2. And as we derived before, that is equal sine square to theta multiplied by sine square delta m square over 4 momental energies of neutrino, now it doesn't matter, multiplied by L, by distance. And this is final expression for the probability. So now we have finally derived this expression for the probability. You see, I used many things here, small step and assumptions, like here, what I was saying that F1 and F2 are equal. F1 equals F2, which means that I neglect completely the possible separation of the shift of the wave packets. Now, if I take into account this, then the situation will be more complicated. But fortunately, the final result is very simple, and you can even derive this in the simplified assumptions that the energy is the same or momenta are the same, even not using wave packet picture, but then some conceptual questions appear usually. So this is without any conceptual question. If you have some questions, ask me. It's interesting that eventually all the traces of wave packet disappear, right? And this is because of this normalization. Now again, the most complicated situation is when you have partial separation of the wave packet. If wave packet is completely separated, then what you will get just averaged factor here, you'll get here 1/2 instead of this sign. If you have complete separation of the wave packets, then making derivation, you will get just this averaged oscillation is 1/2. If you have no separation, no these complications, then you get this formula. Intermediate case is more complicated. And then you will need to know what is precisely the shape of your wave packet to make computations. Let me see what I will do. Let me first, in this 5 minutes, just analyze this formula. What is this? We can depict the probability, and this is transition probability. So because we had one state in initial state, mu E, and this is transition probability. So we can also introduce survival probability. Which means that you emit electron neutrino in initial state and ask what is the probability to still find electron neutrino in your beam. This is what is called survival probability. And this P survival equals 1 minus P transition. So let me put here transition. Okay. Now for transition probability, I have the following picture. As a function of L, right? So what we have here, the depths of oscillation. So I have oscillatory picture, which is coming from this factor, which is from the phase factor. And again, remember, oscillations is the consequence of phase change between mass states. Sometimes there is a confusion that how this one neutrino can be transformed into another because masses are different. Mass composition doesn't change. So amount of nu1 and amount of nu2 doesn't change, and therefore there is no issue of transition from one mass state to another mass state. The only what changes is phase difference between nu1 and nu2. And it is this phase difference which leads to oscillations. So the depth of oscillation is given by sine squared to theta. And of course, the bigger angle, the stronger transition, and the maximal transition, if the theta is 45 degrees, then you will have sine squared to theta 1. which means that you have complete transformation of one neutrino species into another one. You will have oscillations with maximum depths in this case. So in the case of maximum mixing. Now, here is the oscillation length. Just period. This is oscillation length. And oscillation length can be computed as when you have delta phi equals 2 pi. So this is the distance when you have the phase difference 2 pi, right? And your system is coming back to your initial state. And then from expression for delta phi, you will have delta m square, 2 energies, and then L nu, it should be 2 pi. So L equals L nu, which is the distance at which the phase is 2 pi. This is what we call the oscillation length. And from here we find that oscillation length is given 4 pi energy and over delta m squared. So this is the expression for oscillation length. And again, let's see at this. The smaller delta m squared, the bigger oscillation length. So if you want to be sensitive to very small delta m squared, you need to have big distances, big enough distances. So if distance between your source and detector is small, your oscillations will not be able to develop. So you are sitting somewhere here. Okay? And again, it is proportional to energy. The bigger the energy, the bigger the oscillation length. So if you want to be sensitive again to smaller delta m squared, then you need to use smaller energies. Finally, what is the average? An average is just given by average of this oscillatory factor, which is 1/2. And that is equal to sine squared theta, 1/2 sine squared to theta. So this is the average probability. So bottom line, oscillations are the process due to monotonous phase difference increase, right? So neutrino travel and the phase difference monotonously increase with distance or with time, and that leads to oscillations. Mass composition doesn't change in this process. Difference of group velocities leads to separation, and when you have separation of the wave packets, the result is given by these average oscillations. I haven't explored this, but it's easy to see. You have two terms when you compute moduli square. Remember, we compute first amplitude, which is sum of two terms, so there is some interference between these two terms. If you have loss of the coherence, then you just should compute moduli square of the first term, which is minus s multiplied by cosine, plus moduli square of, again, sc with the phase factor. Okay? And then you will get such a result for average probability. The loss of the coherence in this case is equivalent to just averaging of oscillations. Now, I think I rushed already a little bit, but at least I finished with this oscillation formulas. Now I want to say still a few words about discovery of oscillations, if you want to listen. Do you want to listen about discovery? I showed already some figures which now you can understand quite easily. So let me still spend a few minutes maybe to describe discovery, at least oscillations. I will have no time to describe conversion of solar neutrino. That's more involved process and more involved consideration.
When wave functions are not overlapping, we do not see this oscillation effect, right?
No. It will be just constant, right? So what you will do is the following. You have detector, and then to your detector, wave packets will arrive at a different time. So it will be a possibility that you will have an interaction of the first wave packet and then the second one. Okay. When you do integration over time, this means that you are doing summation over effects of both wave packets. And then you get this 1/2 sine squared theta.
So when we detect one wave packet, which is very largely separated from the other wave's mass state, when we detect it, we need to detect the flavor state, electron neutron or ion neutron.
Yes.
How it's decided which?
Well, yes, so you will just, if some new one is arriving, suppose you have just new one, suppose new one is arriving, then your signal would be proportional, and your detector is detecting new E. So you have the process when you have new E. And then you ask what is, first of all, overlap of new E and new one, and you will get cosine square theta if you compute moduli square, and this is the probability, which means that only part of your state, right, will produce the signal,
But
which is proportional to new E. Remember that you can invert our mixing formulas, and then new one is given by cosine theta new E minus sine theta new 2, or sorry, new mu, or new A. Right? So you can invert this. And then what happens if you have here the flux of new one, then only this part of your state will produce the signal, which means that the signal will be proportional to this cosine square theta.
so we will see a mixing, but the oscillations are actually not there.
I don't know what you will see mixing. You will see, yes, you will see mixing in this sense that the signal will be suppressed in comparison with full electron neutrino state by this factor.
So when we have neutrons from sun or from some other distant point, they differ in this aspect of probabilities because one is not oscillating, they are not coherent, and the other can be coherent. And
Well, I don't know what you mean, one or another. So here, when you have separation of the wave packets, then both are incoherent. So you have fluxes of nu 1, and you have independent flux of nu 2. So from the sun, we have incoherent fluxes of nu 1 and nu 2, dot. And of course, electron neutrino is also sitting here, part of it, which is proportional to sine theta, right? So this has cosine theta component of nu e, and this has sine theta component. And then you need to sum up, yeah?
at the beginning you said that they have different masses because they are mass states.
Yeah.
And if you don't have enough mass, if you have only enough mass to produce one new one,
Yeah.
then what will we be producing?
Well, you just produce one mass state.
But when we observe it, then
Yeah, you see,
it should
so that of course, I mean, this is like for neutrinos which we know about, this is Gedanken experiment, because masses are so small that in all the process they essentially produce. That would be interesting possibility, because then you really immediately measure this mixing angle, all right? So that has some relevance if you have heavy neutrinos, and people are discussing that maybe there are some new neutrino states which are heavier, say 1 GeV. Certainly these neutrinos will not be produced in beta decay, okay? So which means that you already produce part of the state. So your electron neutrino, which is staying in your charge current or in your Lagrangian, it actually has this heavier component, but it is not produced in beta decay. And so that has various consequences. You will have already a lepton number violation already in the production process, by the way, because you kind of cut part of the state and you have no orthogonality of the light states which you are producing. Well, there are different interesting effects on this. Okay? So let me just very briefly, because I showed already the slides to discuss discovery, at least oscillations. So, as I said, oscillations have been discovered in atmospheric neutrinos. And you saw the processes when we have this chain of pi and muon decays. And what we detect are E-like and mu-like events. And what is expected first is the ratio of mu-like to E-like event in your detector, something like 2, at least at low energies. This is expected. And observed value was 1. However, that was actually already known from 1988, and so that was hint of some problem. But final discovery was in 1998, when at neutrino conference, Kajita-san has announced the results of measuring of zenith angle dependence of mu-like events. So you have the Earth. Suppose your detector is sitting here, and zenith angle is the angle between direction of neutrino. So suppose neutrino is produced here, and this vertical direction. So this is what we call theta z, zenith angle. So neutrinos are produced everywhere in atmosphere, and so you have neutrinos which are arriving to your detector from different directions, like here and also from above, right? You have neutrinos arriving from different directions. And in Super Kamiokande, they can establish what is direction of this your mu-like event. It's just the way how your kind of ring is distorted, how you can find what is the direction. So, what is important that changing zenith angle, you change trajectory or length of trajectory of your neutrino, right? The length of trajectory is given by 2 Earth radiuses multiplied by cosine theta zenith moduli square. So you can just find this from simple geometry, right? So you have this center, and so you can find what is this length of trajectory using the radius and the zenith angle. So you may check this. Actually, we have exercise on this. And therefore, studying zenith angle dependence of your events, you essentially study dependence of your probability, possible probability of oscillations on L. Okay? So, the result was the following. That was number of events observed over expected without oscillations. And it had the following shape. So this is cosine theta zenith. It's -1, it's 1, and 1 is direction from up to us. And the distance from production point to our detector was something like 10-15 kilometers. So this is the width of the atmosphere, or place where these first interactions occur. And so what was finally found is something like this. Maybe something like this. So here no oscillation effects. This is 0. And this direction corresponds to horizontal direction when neutrinos are coming from horizontal direction. So no oscillations here. Here are averaged oscillations. So this is for very long trajectories. So that point corresponds to long trajectories. And you may have here a bit oscillatory effect, but everything is averaged. So what is essentially observed was this averaging stuff. Okay, so that has been found. Well, you can measure this distribution for different energies, right? So you can also measure different energies, and depending on energy, it slightly changes. So for instance, for lower energies, you will have something like this, if you take into account averaging effect. And then what I have shown you, this L over E dependence. Once you know the energy, and they use different energy intervals, and you know what is the length, you can construct L over E dependence of your events. So this is probability P mu mu. And then for this L over E, you have kind of inverted picture in comparison with that. You have 1 here for small distances. Then that's something like this. And then like this. This is what they have observed. And you saw this type of the experimental plot, right? Something like this. Now, without averaging, you would expect such a picture. But due to averaging effect, because first of all you see only muon, you detect direction of muon and the measure energy of muon, but then you need to reconstruct what is an energy of neutrino. So essentially you are doing some integrations and averaging, you have finite energy, angular and energy resolution. So this stuff boiled up to such a curve. So here what you can see is really the first oscillation minimum, clearly. And then it is averaged process. By the way, people suggested even some other explanations, but they had slightly different dependencies here, and eventually neutrino oscillations have been established as a main reason for this effect. Then everything has been confirmed by reactor experiments. Sorry, accelerator experiments, and this was experiment T to K, minus K to K. Then it was experiment opera, and so let me, I forgot, I think something K to K, T to K, minus of. So those experiments measured disappearance of nu mu. So they produce muon neutrino beam, as usually in accelerator experiments, you see its disappearance. Opera observed really transition nu mu to nu tau, but they observed events related to tau. Actually, the final publication was essentially this year. Well, the problem was that we have 3 neutrinos, right? And the question is what muon neutrino oscillates to electron or to tau neutrino, or to maybe to some sterile neutrino. So people discussed different possibilities. And eventually it was established that these are oscillations to tau neutrinos. So what we have here is nu mu to nu tau oscillations. So that is confirmed. Also nu mu also can oscillate to electron neutrino. And delta m square in this experiment is 2.5 10 to the minus 3 electron volts. And surprisingly, the mixing is close to maximal. Sine square to theta is approximately 0.5. Sorry, without 2t. So sine square theta is 0.5. With the error bars is something in between 0.4 to 0.6, and actually the present best fit point corresponds to something like 0.55. So, absolutely different from quark mixing. Quark mixing between the second and the third generation, as you remember, given by VCB, and VCB is 0.04. So if you want to have analogy, you need to square this and multiply by a factor of 4. Very small mixing in quark sector, and very big mixing in lepton sector. So I think I should stop here and please ask me the questions. Yeah. Or maybe you'll ask first.
If we were able to produce neutrons with a definite mass in a definite mass state, we measure it, we won't see oscillations in that case.
No.
Because we always see.
Unless it is in matter. In matter, actually, mass states are oscillating. But anyway, so ask me a question.
Yeah, no, that was my question.
Yeah. So because it's interference effect, nothing to interfere with. Right? So,
and if we were able to detect mass definite states, then in that case, that we produce a flavor state, and then we detect only mass states, we will also detect these two parts coming in like different.
You will not see any oscillations in the first place, and the effect will be proportional to mixing in the beginning. So what you?
But so far we only know how to detect flavor, definite states.
Yeah, that would be great if you suggest how to detect mass states. Well, this is interesting. This is in contrast to quark sector, because in quark sector we usually deal with hadron sector, with mass states, and here, well, nature help us, like to have these mixed states. And yeah, no question.
In quark sector, we have those mixings involved also in the interaction terms, and we can calculate for some given diagrams using those mixing angles.
Yeah.
Here, in this mixing concept, do we see any effect on the interactions with weak interactions or any other?
No. So let me try probably to in quark sector, what is interesting, we deal with mass states. All right, so we have some mass state with strangeness which decays into some other mass states, because coherence is very quickly broken. There is no very small mass differences. So that's the point. In neutrinos, we have these coherent effects, and it is not possible to destroy it, at least for small distances. So in quark sector, we have mass states, in initial and final states, of hadrons. Remember, mixing parameters, they connect different mass states, right, in your charge current interactions. Okay, so this is why we measure immediately in quark sector mixing parameters. Here, we have, for instance, electron, but what we produce is electron neutrino. And therefore, we cannot do the same way as in quark sector, because we produce mixed state. If you would produce just mu one, and we know, so destroy coherence, he wants, suppose we have some way to destroy coherence and then measure mu one, that would be analogy. So we produce something with electron or electron, so which means that we have electron, which is mass state, and then we have mu one in final state, which is again mass state. Measuring this, we immediately measure the mixing angle, like in the quark sector. However, we have, say, electron in initial state, but that it produces mixture of mu one and mu two. But we have some more sophisticated way still to measure mixing.
Yes.
Then we have oscillations which are proportional to mixing angle.
If you don't have the oscillation states separated, V1 and V2, like from solar neutrinos,
No, so we have, yes, yeah.
are they useful maybe to detect the mixing angle through an experiment? Because at least they do not oscillate and they still remain in.
I had no time, unfortunately. You see, there is this part on solar neutrinos, and Art McDonald got a Nobel Prize for these transitions of solar neutrinos. The situation is again another confusion, which also a Nobel Prize laureate kind of committee did. So what we see in the case of the sun is not oscillation really. What I have shown this in these colored slides before. So we have this adiabatic conversion. Anyway, so of course we measure also mixing angle using solar neutrinos. And it is nice that we have very good agreement between mixing angle measured in solar neutrinos. It's not in this way. So for instance, in solar neutrinos, the effect which is measured in this McDonald experiment is proportional to sine squared theta 1, 2, what we call. It's not sine squared 2 theta, but it's sine squared theta. So this is the effect. And of course we measured, yes. And we have a good agreement with Scanland experiment, which is experiment with atomic reactors. I show this stuff. For Camlot, we have really oscillations, and there is a good agreement. Yeah?
So I have a question. What are sterile neutrinos?
Sorry, what?
Sterile.
Well, that actually Pontecorvo invention. So he was saying that neutrinos which have no weak interactions, he called them sterile neutrinos. Because it's in the early days before everything. Now, right-handed neutrinos are sterile neutrinos. You will see this in the standard model course. So we have left components and right components of fermions. So for charged fermions, quarks and leptons, both left and right components participate in weak and electromagnetic interactions. In contrast, right-handed neutrinos, if they exist in the standard model, they have no weak interactions. They have no interactions with Z boson, of course with photon, and also with W boson. No interactions. And therefore they are sterile neutrinos, so nothing is special about this. Sometimes people invent some more sterile neutrino states on the top of this.
And this oscillation also put a bound on the number of flavors or generations of leptons and neutrinos?
Well, the stringent bound comes from lab experiment. Remember, I mentioned this Z0, and you know this, right? So Z0 decay invisible widths. So we can measure this in experiment, and it is in agreement with 3 neutrino species. Of course, always it could be some small admixture of some sterile neutrinos up to a precision of measurements.
And we know that there is only 2, at least for now, to explain 3 generations of flavor. 2 mass states are enough.
Yeah, so one of the neutrinos can be massless.
What are the experiments that want to show to see the hierarchy of the mass?
Oh, it's complicated, you know.
How?
I don't know if everybody wants to listen this. Okay, so for time being, there are several suggestions, and you may establish hierarchy if, say, for instance, tomorrow neutrino burst will arrive from collapse of supernova. So we are expecting this badly. You know, that these collapsing stars produce huge fluxes of neutrinos, and one event has been detected in 87, so-called sigma from 87A, supernova 87A. So that is the signal even not in our galaxy, in satellite galaxy. So if the signal arrives, that we can infer this hierarchy from this supernova neutrino signal properties of the signal first. Now, there are few experiments which are planned. So one is the experiment like Orca and Pingu to use matter effect, and so these are underwater and under ice experiments. So the idea is, but then I need to explain what are these matter effects. Then they are sensitive to neutrino mass hierarchy. Then it was there is an idea. So these two, most probably Orca will be first. So they are doing this. It may be in 2022, 23, 24 they will be able to say what is the mass hierarchy. Well, I can't explain it, but let me get it right. So normal hierarchy, if you have such a situation, this is 1, 2, 3 states. So the state 1 is with the biggest amount of electron flavor. Second is something like 1/3, and in the third state is very small amount of nu E. So I can actually mark my states in this way. Such a situation is possible, but also this one. So this is normal ordering of hierarchy, and this is inverted ordering. So supernova neutrinos, then this Orca and Pingu experiments, and then Juno experiment in China. What they want to do is to have very precise measurements of distortion of energy spectrum from reactors. And measuring this very small, and oscillation have very small depths. This is due to 1,3 mixing, which is small. They can also establish mass hierarchy. And then there's a number of experiments, even further from us, like a Dune experiment or Hyperchemiacand, which aimed also at establishing of mass hierarchy. Actually, the present day experiments already give some hint that hierarchy is normal. And maybe further operation of NOVA experiment in US, it's Fermilab, and then it's Minnesota. They have quite big distance, and therefore there is a matter effect on these oscillations, which is sensitive to mass hierarchy. Nowadays it's something like 2 sigma preference of normal ordering. So they can proceed a little bit more, working and maybe it will reach say 3 sigma, something like this. But I think in the middle of 20s, probably we will find. Unless, again, sigma from supernova will arrive and we will manage. It also depends on a few things. It's just interesting that depending on in which channel you will see mass hierarchy, sorry, Earth matter effect. So these neutrinos may cross the Earth. So if supernova explodes from other side of the Earth, then they cross the Earth. And depending on where you see effect of the Earth matter, in neutrino channel or anti-neutrino, you can say what is the mass hierarchy.